When facing the challenge of driving ground rods indoors and encountering rock, several methods can be employed. Firstly, let's consider using a breaker bar. The necessary materials include a breaker bar, a socket wrench, an 8FD ground rod, a 5/8-inch drive and ground rod adapter, and grounding compound. The steps are as follows. 1. Attach the drive and adapter to the ground rod. 2. Place the ground rod inside the pilot hole and secure it with grounding compound. 3. Use the breaker bar to drive the rod into the rock by applying downward force and rotating the handle. 4. Drive the rod until it is below the floor level. Secondly, we can examine using a sledgehammer. The materials needed are a sledgehammer, an 8FD ground rod, a 5/8-inch drive and ground rod adapter, and grounding compound. The steps involved are 1. Attach the drive and adapter to the ground rod. 2. Place the ground rod inside the pilot hole and secure it with grounding compound. 3. Use the sledgehammer to drive the rod into the rock by striking the adapter repeatedly. 4. Drive the rod until it is below the floor level. Thirdly, the use of a rotary hammer can be a viable option. The required materials are a rotary hammer with a ground rod bit, an 8FD ground rod, and grounding compound. The steps are 1. Attach the ground rod bit to the rotary hammer. 2. Place the ground rod inside the pilot hole. 3. Use the rotary hammer to drill into the rock and drive the ground rod into the ground. 4. Drive the rod until it is below the floor level. Here are some additional tips. Use the sharp ground rod bit to penetrate the rock more easily. Lubricate the rod with penetrating oil to reduce friction. Be patient and use steady force to avoid damaging the ground rod or the floor. Once the rod is driven in, make sure to connect it to the grounding system using an appropriate conductor. The grounding electrode system is a critical component of the electrical system, providing a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. This grounding system is essential for safety, preventing electrical shock hazards and minimizing the risk of fire. The National Electrical Code, or NEC, provides detailed requirements for the installation and configuration of grounding electrode systems. These requirements are designed to ensure that the grounding system is effective and reliable. According to the NEC, a grounding electrode system must consist of one or more of the following electrodes: a metal underground water pipe, a metal frame of the building or structure, a concrete encased electrode, a ground ring, or ground rods and pipes. Ground rods are a common choice, especially in residential and small commercial installations, due to their relative simplicity and cost-effectiveness. When driving ground rods, it is crucial to adhere to NEC guidelines. NEC Section 250.53. She specifies the requirements for ground rod and pipe electrodes. The electrode must be at least 8FT in length and must be driven into the ground to a depth of not less than 8 foot. The upper end of the rod must be flush with or below ground level unless protected against physical damage. In situations where rock or shallow soil prevents driving the rod to its full length, the rod can be buried at an angle not exceeding 45 degrees from vertical or buried in a trench at least 30 inches deep. The spacing between multiple ground rods is also important. NEC Section 250.56 requires that when 2 or more ground rods are used, they must be spaced at least 6 FT apart. This spacing helps to minimize the overlapping of their effective grounding zones. The purpose of a grounding electrode system is not to carry current under normal conditions but to provide a path for fault current. Therefore, the resistance of the grounding electrode system should be as low as possible. The NEC requires that the resistance to ground of a single ground rod must not exceed 25 ohms. If the resistance is higher than 25 ohms, a second ground rod must be installed. The two rods must be spaced at least 6 FT apart. The 25 ohms requirement is intended to ensure that the grounding system provides an effective path for fault current to flow back to the source, allowing the overcurrent protective devices to trip and clear the fault quickly. The connection between the grounding electrode and the grounding electrode conductor is crucial. NEC Section 250.70 specifies the requirements for this connection. The grounding electrode conductor must be connected to the grounding electrode by exothermic welding, listed lugs, listed pressure connectors, or other listed means. The connection must be permanent and mechanically strong. The size of the grounding electrode conductor is determined by NEC Table 250.66, based on the size of the ungrounded service conductors. The grounding electrode conductor must be sized appropriately to handle the maximum fault current that could flow through it. The grounding electrode system must be properly bonded to the building's metal components. This bonding is essential to ensure that all metal parts are at the same potential, minimizing the risk of electrical shock. NEC Section 250.104 specifies the requirements for bonding metal water piping systems, metal gas piping systems, and other metal components. These metal components must be bonded to the grounding electrode system with a bonding jumper sized according to NEC Table 250.102. In some situations, it may be necessary to supplement the grounding electrode system with additional electrodes. This is especially important in areas with high soil resistivity or where the soil is dry or sandy. Additional electrodes can include concrete encased electrodes, ground rings, or chemical ground rods. Concrete encased electrodes, often referred to as U-for-grounds, are installed within concrete foundations. They provide a large surface area for contact with the earth, resulting in a low resistance ground. Ground rings consist of a bare copper conductor buried in a continuous loop around the perimeter of the building. Chemical ground rods contain chemicals that leach into the surrounding soil, improving its conductivity and reducing the resistance to ground. The installation of ground rods can be challenging, especially in rocky or hard soil conditions. Several techniques can be used to overcome these challenges. One technique is to use a ground rod driver, which is a tool that attaches to a rotary hammer or demolition hammer. The ground rod driver provides a powerful hammering action that helps to drive the rod into the ground. Another technique is to use water to soften the soil. By pouring water around the ground rod, the soil becomes easier to penetrate. It is also important to select the right type of ground rod. Ground rods are typically made of copper-clad steel or galvanized steel. Copper-clad steel rods offer better corrosion resistance and are generally preferred. When driving ground rods near underground utilities, it is crucial to exercise caution. Before driving any ground rods, it is essential to contact the local utility companies to locate any buried cables or pipes. Striking an underground utility can be dangerous and can result in service interruptions. The grounding electrode system must be inspected regularly to ensure that it is in good condition. The connections must be checked for corrosion or looseness, and the ground rods must be inspected for damage. If any problems are found, they must be corrected promptly. The grounding electrode system is a critical component of an electrical system, providing a low impedance path for fault current to return to the source. By following the NEC guidelines and using proper installation techniques, it is possible to create an effective and reliable grounding electrode system. Remember to always prioritize safety when working with electrical systems and consult with a qualified electrician if you have any questions or concerns. Now let's delve deeper into the specifics of the methods described. When using a breaker bar, the primary advantage lies in its ability to exert significant force in a controlled manner. The breaker bar's leverage allows for a steady, powerful push and rotation, which can be particularly effective in breaking through smaller rock fragments or compact soil. The socket wrench is used to secure the drive and adapted to the ground rod, ensuring a solid connection that can withstand the force applied. The grounding compound serves multiple purposes. It helps to fill any gaps between the ground rod and the surrounding soil, providing better electrical contact. It also helps to reduce corrosion of the ground rod over time. The act of placing the ground rod inside the pilot hole is crucial for guiding the rod and preventing it from bending or deflecting during the driving process. Securing the rod with grounding compound before driving further stabilizes the setup. Applying downward force and rotating the handle of the breaker bar simultaneously is key to effectively driving the rod. The rotation helps to break up the soil or rock, while the downward force pushes the rod deeper. Driving the rod until it is below the floor level ensures that it is protected from physical damage and that it makes good contact with the earth. When employing a sledgehammer, the impact force is the primary mechanism for driving the ground rod. The sledgehammer provides a powerful, direct force that can be very effective in breaking through harder rock formations. A drive-in adapter is essential for protecting the top of the ground rod from being damaged by the sledgehammer blows. It also helps to transfer the force evenly across the rod. As with the breaker bar method, placing the ground rod inside the pilot hole and securing it with grounding compound is crucial for stability and electrical contact. Striking the adapter repeatedly with the sledgehammer requires precision and control. It is important to maintain a steady rhythm and to avoid glancing blows that could damage the rod or the adapter. Again, driving the rod until it is below the floor level is necessary for protection and optimal contact with the earth. The rotary hammer method offers a more sophisticated approach, combining drilling and hammering actions to penetrate the soil and rock. The rotary hammer with the ground rod bit is specifically designed for this purpose. The bit is typically made of hardened steel and has a special shape that allows it to drill through rock and soil efficiently. The drilling action helps to create a path for the ground rod, while the hammering action helps to drive the rod deeper into the ground. Placing the ground rod inside the pilot hole is still important for guiding the rod, but the rotary hammer's drilling action makes it less critical than with the other methods. Using the rotary hammer to drill into the rock and drive the ground rod requires a steady hand and patience. It is important to apply consistent pressure and to avoid forcing the tool. Again, driving the rod until it is below the floor level is necessary for protection and optimal contact with the earth. Now let's revisit the additional tips provided earlier. Using a sharp ground rod bit is crucial for penetrating rock more easily. A dull bit will require more force and will be more likely to slip or break. Lubricating the rod with penetrating oil can significantly reduce friction between the rod and the surrounding soil or rock. This makes it easier to drive the rod and reduces the risk of bending or damage. Being patient and using steady force is essential for all three methods. Avoid rushing the process or using excessive force, as this can damage the ground rod or the surrounding structure. Once the rod is driven in, making sure to connect it to the grounding system using an appropriate conductor is the final step. The conductor must be sized according to the NEC and must be securely connected to the ground rod and the grounding system. Choosing the right method depends on the specific conditions of the installation site. If the soil is relatively soft and the rock is fragmented, the breaker bar may be sufficient. If the rock is harder and more solid, the sledgehammer or rotary hammer may be necessary. Ultimately, the most important thing is to follow the NEC guidelines and to use proper installation techniques to ensure a safe and effective grounding system. Also, always verify all dimensions against the local and national code requirements, as they may vary. Also be aware of all underground utilities, such as gas lines, water lines, and communications lines, to avoid any injury or service interruptions. Call before you dig.